Hello everyone. So we're going to start section 14.7 covering maximums, minimums, and saddle points. And before we start, let's just quickly review that in 14.6 we ended with the gradient vector of a function. And for a particular point, you plugged it in and it was pointing in the direction where z will increase the fastest. And then the opposite direction, so the negative of the gradient, was pointing in the direction that z decreases the fastest, right? So let's consider this function here. And remember that to find the gradient, you take the partial with respect to x and then the partial with respect to y, since this is only a function of two variables. And so that's how we get these expressions here using the partials. And so what we want to do is let's plug in particular points and let's just kind of see what's going on with this function. So if I plug in the point 1, 1, which is right here, if you plug it into the function, you get that your output z value is 6. And so therefore, this is corresponding to a point on the surface with coordinates 1, 1, and 6. But when you plug it into the gradient, what you're getting is its corresponding gradient vector. And so I'm here at this point, and if I'm standing on the point on the surface, which is 1, 1, 6, the gradient is telling me that I should walk in this north direction for me to have z increase the fastest. And then if I negate this vector and I go in the opposite direction down, I would have z decrease the fastest, right? But let's just keep talking about z increasing, so I don't keep going back and forth. So that's this point. This is a corresponding gradient vector, and so we should walk this way for z to increase the fastest. Now, if I consider a different point and I plug that in, so let's say the point 3, 4, and I plug that point into my function, now I get the output value z is 5, and so the corresponding point on the surface is 3, 4, 5. And so if I'm standing at that point on the surface, and now when I plugged in this point here into the gradient, I'm getting its corresponding gradient vector, which is now telling me I need to walk in this direction. So if I'm standing on the surface at the point 3, 4, 5, and I walk in this direction, now my z value is going to be increasing the fastest if I'm located above this point, right? And so what I want us to do is, our goal is going to be to find maximums and minimums. And since the gradient vector points where your z values increase the fastest or they decrease the fastest, they're going to give us some insight on how to search for these maximums and minimums. And so what I want us to do is I want us to consider a general point x, y, and see how the gradient vectors change depending on what you're plugging them in. So let's do this on GeoGebra with this exact function that we've been playing with. So here I have the function, and on the right side of the screen, I have the xy plane, which is what we were looking at earlier. And then on this side, I have the same thing, except that we're visualizing it in 3D now. So here's the positive x-axis and the positive y-axis, okay? So let's see what happens. Whoops, let's make this guy go away. Let's see what happens if we vary our points. And notice what the gradient vector is doing. So as the point is getting farther away, notice that this point here is going up. And so the gradient vector is telling me keep walking this way, keep walking this way. But now once I get to the other side, it starts pointing in the other direction, right? So now notice that your gradient vector is pointing that way, which is exactly what this is doing. And so let's say I stop the x value from changing, and now I wanted the y value to change. So now it goes over, and then notice that your gradient vector is saying keep walking that way, keep walking that way. But then all of a sudden, now it's telling me to keep walking down, and I want you to notice what's happening to the point C right here, okay? So notice that it was kind of slowly wanting to go down, and then now it's coming back. So now your gradient vector says, oh, keep walking up, keep walking up. So let's do it again. So it's going to go back this way. It's going to go back, telling us to go up, and notice that your point C is going up. And then when it starts to kind of reach a peak, and then it starts to go down, notice that the gradient vector says, go back. Go back so that you can keep increasing your z value. And so let me stop that, and let me change my x value here. So now let's say the x value is here, and we're changing the y value again. So notice that the point C is going to go up, and so your gradient vector is telling you, yep, keep going up, keep going that way, keep going that way, but you should be walking more towards the left-hand side if you want to keep increasing even more. And so if we pause it, now it's telling me that if I walk in this direction, I'm going to increase Z the fastest. So let's see, if I increase my, if I walk in this direction, my X value is decreasing. So if I decrease my X value, notice that my point C is going up. So it is true, it should be going that way. And now it's telling me, hey, you know what? Keep decreasing your X value by a little bit, but also keep decreasing your Y value by a little bit. So if I decrease my Y value, notice that it went up, and it went up. Oh, and now it's telling me to increase the Y value. So if I keep going this way, so notice that now it's not telling me to change the Y value, it's telling me to keep decreasing the X value. So if I decrease it just a little bit, oh, that gradient vector gets shorter and shorter and shorter, and now it turned around once it reached to X value 0.8, 0.9, oh, it's getting very short. Oh, it will let me do it, probably not. So it looks like if the X value is about 1 and the Y value is about 3, the gradient vector starts to get smaller because it doesn't want me to walk in the direction as much, because it's telling me that I'm pretty close to a peak on my surface, because it's hard for this point to keep increasing. And so let's look at the surface and notice that that's exactly what was going on. As your gradient vector started to get smaller and smaller and smaller, meaning its magnitude started going to 0, your C value started reaching a peak or a maximum. But now, if your point is very far away from this peak, the gradient vector is telling you, nope, nope, keep walking towards the left, so you can start increasing your Z value even more. Versus if I have an X value on this side, notice that now it's telling me to go to the right because now the point is on this side, is on the left side over here, right? And so what I want us to notice is that when we were reaching a peak, your gradient vector started to approach the 0 vector, because once you reach a peak, there's no way for that Z value to keep increasing since you're at a peak at that point, okay? And so that's what I want us to look at. That's what's going to happen. So let's take a look at a different function. So now let's consider this function, which is different. Now it's a degree 4 polynomial, and here is its gradient. And so I want us to see what's going to happen with this one. So let me go back. I'm going to close all these so we don't get confused. So make them go away. Okay. And so let me close this real fast. Let's see if it'll do it for me. If not, it's fine. Okay. So now we're going to do the same thing that we just did with the gradients. Okay. And I want us to, let's see, I don't think it's going to let me scroll down. It's okay. So notice at the point, whoa. I want us to look at the gradient and notice that it's telling me go in this direction, and I want you to also keep track of the point in terms of how it's increasing. Whoa, it increased and went down. Right, so there's something going on there. Okay. So it looks like there's a peak once I get close to that. All right, cool. And it keeps going down, so it keeps telling me to keep traveling in this direction because it looks like this is the direction that will help my my Z value increase. Okay, let's change the Y value. Let's see what happens. Oh, now it's telling me to walk in that direction. Okay, yep. So let's see. Let me pause it here, and let's see. So now if my so now look, notice that when my Y value is down here, it's telling me to walk in this direction to increase. So let's say I keep decreasing my Y value. Oh, sorry, my X value. And it keeps going and it keeps going and it keeps, whoop, there was a switch. So it keeps telling me to go to the left, but now when I go like this, it tells me to go to the right. So that tells us that there's probably some kind of, and now it's telling me to go down, versus here it was telling me to go up. So let's see, maybe there is something going on over here at the point -1, -1. That's telling me to travel this direction to reach to have z increase the fastest. But now when my y value gets even lower, now it's switching this way to increase the fastest. So probably something's going on over here. Let's see here. So whoops. What about if I move my x value? Okay, so now instead of it having me go towards the point -1, 1, it's telling me to walk this direction. Okay. Whoa, and now it's telling me to walk this direction. Okay, so some funky stuff's happening over here. Let's see, let me decrease my, whoa! Okay, so now I decrease my y value, and now it's telling me to go this way. So something weird's going on with this one. It has more than one maximum. Oh, the vector is getting smaller. It's getting close to the zero vector. Okay, so since this is getting very close to the zero vector, there's something going on here. Let's see, where else can it be getting smaller? Nope, bigger, bigger, bigger. Nope. Oh, it's getting smaller. Oh, okay, that's pretty close. Oh, and now it's switching directions. Okay, so it's telling me to walk this way, but then it tells me to walk this way. So something's going on over here as well. So let's take a look at the surface. Oh, wow, look at this one. Okay. So there seemed to be two peaks going on, which is probably where the switching thing was going on here and here. And then the origin, it was also getting very small. So let's see, can I get close to those peaks? Yep, when I get close to those peaks, notice that depending on the side you're on, your gradient vector says, nope, walk this way or walk that way, because it wants you to keep walking towards the peak. And then when we were at -1, -1, -1, it was doing something similar where it kept switching on us. So it's going down and then tends to go back up, because now it wants you to go this way or go down, depending if you pass the peak or not. Whoa, 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 whoa. Okay. Now at the origin, let's see if I get close to the origin. Let's see, will it? Yeah, see the vector is getting smaller and smaller and smaller there. And so this is happening at this weird, it's not a minimum exactly, and it's not a maximum. We're going to talk about that. This is what's called a saddle point. Think of it as a saddle that you put on a horse and you sit on it, right? So notice that our gradient vector is also approaching the zero vector there as well. All right, good. So let's see what's going on. It looks like it approaches a zero vector at peaks, at these saddles, and it will do the same thing for minimums, okay? All right. So let's see. Let's give these things formal definitions. So it says a function f of two variables has a local max at a point AB if the output value at this point is greater than or equal to all the other output values for points near AB. Okay, so when you're very close to point AB, the output value or the z value associated to that point is the greatest one for all the other z values around them, right? So it's kind of like you got, let me see, did I draw? I think I drew it earlier. No. So it's kind of like you got this little peak going on right here. As you're getting close to the point, here's a point AB, and these z values around here, this z value, f of AB, is the winner. It's the highest one for all the other z values around it. Okay. And similarly, we have a local minimum at your point AB if the z value associated to that point, or its output value, is less than or equal to all the other z values for points near AB. So here it's the opposite. So here's point AB, and let me do it over here. You got something going on like this, and then here's your point AB, and then you plug in all the z values near it, but the output value of AB is the smallest one around the other z values. And that's kind of what this is saying. So this is a local minimum, right? When you're close to the point AB. Far away, who knows? There might be something even lower. But when you're close to that point, its output is the smallest one around there. Okay. And so if the output value of AB is greater than or equal to all the other z values for all of the points in the domain, that means, for example, this output value would be the biggest one out of the entire z values on the surface. We say that f has an absolute maximum at this point. And same thing with absolute minimum. If the output value at AB, or that z value, is the smallest one, so less than or equal to all the other z values for all the other points in its domain, we say f has an absolute minimum, okay? So that's their formal definitions, so keep that in mind. So thus, for a function f, if f has a local max or minimum at a particular point, what we notice on GeoGebra, and turns out to be true, is that the gradient vector will be the zero vector at that corresponding point, okay? And so what we're going to want to do is to find local maximums and local minimums, possible points where we can have a local max or minimums are points where the gradient vector will be zero. And it's going to take, this is going to sound a little bit like Calculus 1, but now with this new Calc 3 material. So we're going to call those critical points. So a point AB is a critical point of your function f if the gradient equals 0 at this point, which means that the partials of x and the partials of y at this point both equal 0, right? Because that's how this vector is defined, with these partials. And if they both equal 0, that's the same thing as saying that this is just the 0 vector. The other possibility of getting a local max or local minimum, a possible candidate, right? Doesn't have to be a local max or local minimum, but where it could happen is if the gradient itself is undefined, because you might end up with some kind of cusp or cone looking shape here. And at this point, your function won't be differentiable, and so your partials won't exist, okay? And there's other weird scenarios, but this is like a visual example to show you where you can have a local maximum, but in that case, your gradient vector wouldn't exist, okay? Okay, so finding out points where your gradient is the zero vector or where your gradient is undefined will give us possible points A, B, where we might have a local max or a local minimum. So let's take a look at the first example that we looked at, that was a paraboloid. So we had this function here, and remember we found the partial with respect to x and the partial with respect to y. That was these guys. And we want to see when they're equal to 0, right? So this, for what you're going to end up with, is usually a nice little system of equations, okay? This one's not so hard because you just have to see what satisfies this equation, and it's when x equals 1. What satisfies this equation? It's when, whoops, this should have been a y here. Let me fix that. That is when y equals 3. And so this is telling us that at the point 1, 3, this is a critical point. We saw earlier on GeoGebra, on that paraboloid, that when we were close to the point 1, 3, our gradient vector was becoming 0. And that's exactly, now we're algebraically showing that yes, it actually is the 0 vector at this point. And from the graph that we saw, we noticed that that was a local max. But not only that, because it was a paraboloid, it turns out to be an absolute max. Absolute max. But we only knew these results because of the graph, okay? This is just algebra showing us where we could possibly have that happen, and it's at a critical point, and it turns out that it was a local max, okay, at the point. So this process is going to help us figure out where we can have possible maximums or minimums, or as we saw earlier, saddle points, which I'll talk about later. The other thing I want to say is because the partials are polynomials, they're always going to be defined, so there will be no points that satisfy this restriction or this condition of your gradient being undefined, okay? So that one doesn't give us any points, versus this one gives us critical points when the gradient is 0. Okay. Now let's take a look at the second problem, where we had this like saddle with two little peaks happening. So here, this one's a little more complicated. Here, your function was of degree 4. Here, we took the partial with respect to x and the partial with respect to y. And now, each partial uses both variables. And like I said, we have a nice little system of equations here. Here, what you can do is you can move this term to this side, then divide by 4, and then you end up with this equation, which is equivalent to this equation. And then here you move the negative 4y cubed to this side, divide by 4, and you end up with this other equation. And so you could do a couple different, you can approach this in different ways from here. But what I did is because y equals x cubed, and the second equation tells us that x is equal to y cubed. Let's see here. Oh, no, I think I made a little mistake here. Let's see. If we substitute this in here, this will be equal to y cubed cubed. And so then we would get 3 times 3 is what, the 9th? Let me double check this. Hold on. Cube divided by 4. Yep. Divide by 4. All right, so let's fix that. No worries. Okay, so then this should be to the 9th. To the 9th here. And so then let's see. Let's just do it all over again right here. No worries. Okay, so it should be to the 9th. And so then I subtract the y on this side. And then if we factor out this y, we get y to the 8th minus 1. And so then when we factor this out, as I notice here, you don't want to divide by y, guys, okay? You want to be very careful, because if you divide by y, you're going to lose a possible y value where you have a critical point. Like notice here, instead, I minus the y to this side, and I factored it out. And by doing that, now I'm getting that what satisfies this equation is when y is 0, or when this is 0, which happens only when y will be plus or minus 1. So it happens when we get plus or minus 1. But if you would have divided by y, you would have lost this piece here, which notice now is going to become an important part for a particular critical point. So be careful when you're doing this. Do your best not to divide, and instead do factoring. Okay, so let's see. So now we have the y values where we're going to have critical points. So since x is equal to y cubed, when y is 0, I get 0 cubed, which is just x equals 0. And so then that gives me that y is 0, x has to be 0, and so I have the critical point 0, 0, which would have not been a point I would have found if I would have divided by y. Okay, so be careful. When y is positive 1, I cube the positive 1, which just gives me positive 1. So then I get the point 1, 1. When y is negative 1, I cube negative 1, and then I get negative 1 again. So I get another critical point. And so for this problem, I ended up with 3 critical points. Now, we don't know, from here, you won't know if you're reaching a maximum, a minimum, or as I said, this weird like saddle thing that's going on. But because in this example, we did look at the graph, we do know that at 1, 1 and negative 1 and negative 1, we had local maximums, right? And I believe from the graph, they also turned out to be absolute maximums. That won't always happen. That was just for these examples. But so now the question is, okay, so I have that this is local maximums, where this one wasn't giving me a maximum or a minimum. That one was giving me what I called a saddle point, okay? And so what saddle points will end up looking like are, like I said, like a saddle, and this is the part of the saddle that you sit in. And so at a saddle point, if you end up finding a saddle point, your gradient will still be 0 there, but we don't have neither a local max nor a local min, because if I consider, let's say this is my point AB here, if it was a local max, that means that for all other z values associated to the points around AB, this guy should have the highest z value, but it doesn't because there's more over here, right? Um, but why is it not a local, wait, I think I said that opposite. If it was a local max, this guy would have, this z value would be the highest for all the other z values around it, and there's larger z values. Oh no, I did say that right. And it's not a local minimum because if it was a local minimum, it would have the smallest z value for all the points around it. But if you notice that this saddle goes like this as well, there are other points near it that have smaller z values, and so that's why it's also not a local minimum. So this is kind of shape that goes on like this, on this direction, and this concave up-looking shape in the other direction. And so that's why it's not neither a local maximum or a local minimum, okay? So the question is, well, if I was to find these 3 points, how can I determine, without looking at the graph, what's going on at those 3 points? And so that will be covered in the following video, all right? Take care. I realized I forgot to give you guys an example of where the gradient does not exist. And as we said, it might look like some kind of corner or cusp. So I wanted to show you an actual example. Here's this function, which turns out to be the function of a cone. But let's say you didn't know it. You didn't know it was a cone. You take the gradient, and this is the partial with respect to x. This is the partial with respect to y. And so notice that it's going to be undefined at the point 0, 0, even though the point 0, 0 is in the domain of the function, right? So it is a valid point to plug in, but for the gradient, it is undefined there. And so if we look at the graph now, notice that this would have given you the critical point 0, 0, and we see here that you do have a local maximum, which in this case turns out to also be an absolute maximum. So here's just an example of algebraically, you might end up finding a point where the gradient is undefined. All right, thank you.